Hello, this is Dr. Simon Romero and I'm here to present you section 13.2, Integrals of Vector Functions and Projectile Motion. In this section we're going to follow these topics and these are the practice problems. I suggest you to do them all. I'm going to start with position, velocity, speed and acceleration, but before that I have to give you a disclaimer. I will be presenting you things that you have seen in your physics classes. Please use the notation that I'm using here as well as the method that I'm using here when you are doing an activity or you are in a celebration of learning. Otherwise, I will not be able to award you the full credit. So let me start. If a vector function represents the position of an object in the space, we say that r of t is the position function of the object. Once you have a position function, then the derivative is we're going to call it the velocity function, and the scalar function, that is the magnitude of the velocity, is going to be the speed, and the derivative of the velocity is going to be the acceleration. The only thing that I want you to note here is that velocity and acceleration are going to be vector functions, and the speed is going to be a scalar function. Integrals of vector functions. So we are going to have two types of integrals of vector functions. We're going to have indefinite integrals that are going to be the collection of all antiderivatives. In other words, the thing that we're going to say is it's going to be one antiderivative plus a vector constant. You will see later that what this means is that we are going to have three constants of integration, in different constants of integration in each one of the component functions of your antiderivative. The definite integral of a vector function is just going to be the definite integral of each one of the component functions. Indefinite integrals are going to be helpful to find position functions, a position function of the object given its velocity and some initial condition. Actually, we're going to go more than that. We're going to start with an acceleration function and we're going to come back doing indefinite integrals to the position function of the object, given that you have some conditions. The definite integral no longer represents any kind of area since the result of this definite integral happens to be a vector. So the definite integral is not going to be very useful for the things that we're going to do in this section. So let me give you an example of how the indefinite integral works. So find the position function of a particle whose position and velocity are these two vectors and whose acceleration is this vector over here, vector function. So let's start writing what we know. We know the acceleration function and we know two very particular positions at 0 in this case. These two are called initial conditions. They are called initial conditions not because they are when t is equal to 0, but because they are particular conditions that are given to us at the beginning of the problem. So in other words, these could be at t equal to 1 instead of t equal to 0, and they still will be called initial conditions. So note that we can use the indefinite integral to find how antiderivatives of a of t look like. In other words, the thing that we have is b of t is equal to that, but we know that all antiderivatives of a of t are given by taking the indefinite integral of each one of the component functions. And notice that here we have three constants of integration that are different. That comes from the constant of integration that was a vector in the previous slide. So I'm using a little bit of notation here because one side is just one antiderivative and the other side is the collection of all antiderivatives, but it's helpful because this antiderivative has to look like that because it's part of the collection of all antiderivatives. So the only thing that we need to do is we need to find what is b1, b2 and b3. So we need b1, b2 and b3, the particular antiderivative that satisfies this condition. That's what we want to find. How do we do that? Well, we put the two pieces of information together. We know that b of t has to be of this form, but we know on the other hand that b of 0 is equal to this vector over here. So we have this vector over here has to be equal to the result when we plug in 0 as t. So notice that after doing this, the thing that we have is that this vector has to be equal to this vector, and then we just set the components equal to each other, and we end up that b1 has to be equal to -1, b2 has to be equal to 3, and b3 has to be equal to 2. So finally we found b1, b2, and b3, and that gave us the velocity vector. Once we have the velocity vector, we're going to do exactly the same thing. Note that to find b of t, we only needed a of t and 1 in the initial condition. So now how we're going to find the position function is going to be exactly the same. We're going to take our velocity and we're going to try to find the antiderivative r of t that satisfies this particular condition. So first we find all antiderivatives, so r of t has to be part of all these antiderivatives. Notice that my constants of integration are different. I called in the previous slide the constants of integration b1, b2, and b3 because they were the constants of integration of the velocity, and I am calling these ones r1, r2, and r3 because these are the constants of integration of r. So using the initial condition again, the only thing that we have is we have to find r1, r2, and r3. So I'm going to plug in t equal to 0 in this case. And why t equal to 0? Because that's the time that they gave us the initial condition of. So given that, we're just going to compare what are the resulting components in each one of the sides, and then we're going to just set the components equal to each other, corresponding components equal to each other, and we obtain that our answer is r1 equal to 0, r2 equal to 0, and r3 equal to 2. So therefore we have that our vector function is equal to this function over here. Notice that this function is obtained by just replacing r1 by r1 in the formula for rt, r2 by r2, and r3 by r3. Note that every integration that we did use an initial condition. So usually if you want to come from acceleration to position, you need two pieces of information. If you are coming from velocity to the position, you only need one. Let me talk to you a little bit about projectile motion. So we have this problem. You have a 1 kilogram projectile is launched from a platform 2 meters above the ground. It's launched northwards, and it has an initial speed of 300 meters per second and an angle of elevation of pi/4 radians above the horizon. If the wind applies a force of 3 newtons to the east, find the position function of the object. So the first thing that we have to do is we have to set up our variables. We have to start translating the words into math. So in this case, the x-axis is going to run from west to east, the y-axis is going to run from south to north, and the z-axis is going to run from downwards towards upwards. Now you have to be careful when you set up your variables in order to make your axis compliant with the right hand rule. Otherwise you're going to have the signs switch. So let me continue. Note that this movement has a constant acceleration. A of t is equal to this. The reason why it has constant acceleration is because you have just two pieces that are giving you, or two things that are influencing in the acceleration: the gravity, of course, and the wind. So usually that's going to happen in these kind of problems, unless it's a very advanced problem. The thing that you're going to have is your acceleration is going to be constant. In this case, the wind and the gravitational acceleration. Once we have that, well, we have the acceleration, we can compute how the velocity is going to look like. So taking the indefinite integral, we obtain that the velocity is equal to this. Notice that we have our 3 constants of integration, and our goal is going to try to figure out those 3 constants of integration. So we have these, and we have our 3 constants of integration. Now the initial condition here is a little bit hidden. It's not explicitly said what is the initial velocity, but we have enough information to know what's going on. So we can try to figure out what else do we know about v of t. So we know that v of 0, just by plugging in here, gives you v1, v2, and v3. So again, if we find our initial velocity, we can find v1, v2, and v3 for this case. Now we know that projectile is launched northward, so that means that you don't have the initial velocity doesn't have a component to the east, therefore the x component has to be equal to 0. So finally we know that v1 is equal to 0. We know that the angle of elevation is pi over 4. That means that the components v2 and v3 have to be equal, so you have to v2 has to be equal to v2. And finally, we're going to use the third piece of information, that is the speed. We know that the magnitude of v0 is equal to 300. So, but on the other hand, this is equal to the magnitude of this vector, that happens to be this. So at the end, we end up that v2 is 300 over square root of 2. So we can conclude that the velocity is equal to that. And now, it seems that 2 is missing right here, so let me just put it really quick. Okay, now that we can conclude that, then integrating again, we have that r of t is equal to this. Notice again that the thing that I'm doing here is I'm putting the integration constants, and our goal is trying to find these integration constants. Fortunately, we do have an initial condition for the position. That means that r of 0 is equal to 0, 0, 2. So using our initial condition, r of 0 is equal to 0, 0, 2, we just plug in for t equal to 0 in the position, and we obtain that r1 has to be equal to r2, has to be equal to r3, and has to be equal to 0. So therefore, we have that, and this is not the velocity, this should say, I'm using the wrong marker, so let me just try to get the right marker. So it says that r of t has to be equal to this formula right here. Well, I think that this is all. Thank you very much for your time, and I will see you tomorrow.